In this video, we present a work that has been accepted to Real-World Surveillance, Applications and Challenges workshop at WACV 2022 conference. DIOR, Distilled Observations to Representations for Multi-Object Tracking and Segmentation. MOT aims to precisely locate and associate objects in videos and has long been a crucial topic in the field of autonomous driving, security monitoring, intelligent transportation systems, and smart city. In recent years, performance of the bounding box-based MOT algorithms are saturated. However, tracking remains a challenging issue. Further improvements will only be possible when moving to the pixel level. Therefore, the researchers start to think of all three tasks, detection, segmentation, and tracking, as interconnected problems that need to be considered together. And it comes to our task, MOTS, multi-object tracking and segmentation. By integrating the segmentation to tracking, the MOTS pushes the research into a new stage. The feature sources used for tracking algorithms are not only including the object-level information, for example, categories, bounding box location, and size, but also the pixel-level features, which are boundary, foreground, and background. However, pixel-level information is sometimes overabundant. How to integrate both levels becomes a new challenge. Thus, an attention mechanism for extracting, fusing, and balancing the multi-level features is necessary for the MOTS to avoid information redundancy. On the other hand, about the network structure design, there are two main streams in tracking nowadays. One is tracking by detection, and the other one is joint tracking and embedding learning. We take advantages of the latter one, which is efficient and jointly optimizable. Also, we use a two-stage detector for better detection performance. Finally, in the full-body bounding box tracking, we use intersection over union as a distance measurement. However, this might not be suitable when we are tracking with the visible part only in MOTS. Therefore, new metrics are required. The figure shows the workflow of the proposed method. Video frames are sent into the temporal feature distiller sequentially in a sliding window in clips, utilizing the adjacent frames to concentrate on the area with objects in the keyframe. It complements the detection difficulty caused by occlusion and ensures the consistency of features longitudinally. The generated club-level feature for the target object is distilled to emphasize the foreground with spatial attention, eliminating the redundancy of the background. Finally, the features are associated with Hungarian matching efficiently. We will introduce each component in details in the following slides. The temporal distiller is mainly achieved by a temporal attention module, which is to smooth the embeddings time-wisely and distill context information to focus on the objects on the scene. Feature maps of the three consecutive frames generated by backbone are concatenated, and 3D convolutions are applied to couple them in the time dimension. Then softmax is performed over each pixel location to generate the temporal attention maps, which are used to create the temporal attention feature that is the weighted sum of the original backbone features. Then the center frame's appearance feature and the weighted temporal attention feature are concatenated and fused by a 3D convolution. Here we show two examples of the TN maps. The first column is the input images and the second column is the temporal attention maps. In the left example, the man labeled in red bounding box is occluded by a lady in the green shirt in frame T-1 and frame T. The feature of frame T is unclear on this bounding box area, Thus, higher weights are learned from frame T plus 1, which can supplement the center frame. On the right, the lady on the pink top is gradually occluded, and we observe weight decay in the 3 adjacent frames. The result shows that, since there are no abrupt change in the background, and object occlusion as well as motion blur are the main causes of mask discontinuity, incorporating the neighboring frames' features could be a useful supplement. Besides, for partially occluded objects, temporal feature distiller learns to borrow information forward and after, thus increase the recall of detection. In the MOTS scenarios, the crowd is much denser than common object segmentation scenes, such as those in COCO. Therefore, it is likely to include multiple objects within the same bounding box, resulting in erroneous segmentation results. Here, we use the spatial attention module to highlight the boundary of the objects, and then dispatch the foreground and suppress the background, so that more concentrated instance appearance feature could be obtained. As shown here, the ROI features for objects are pulled and flattened for classification and bounding box regression. Simultaneously, they are passed through a spatial attention module to generate a spatial attention map. A 2D convolutional layers shared with the mask hand is used to generate attention weights and followed by a pixel-wise sigmoid operation. The values in assay map indicates the probability of obtuseness. Then the attention feature is concatenated with the ROI features and are passed through some convolutional layers to obtain instance-level embeddings. Here we show some examples for assay map visualization. For each object, the left figure is a cropped and resized bounding box on the raw image, and on the right is the corresponding spatial attention map. The assay maps highlight the foreground of the proposals and suppress the noisy background, helping to extract more purified and task-specific appearance features. The objective function of DIOR network has 4 components: smooth L1 loss for bounding box regression, cross-entropy classification loss, binary cross-entropy loss for segmentation, and the loss embedding is the cross-entropy loss for identity recognition, which helps to generate more distinctive embeddings. Features of each track are represented as an online updated stack of its features of the first 5 frames and the most recent 5 frames. We first use a Hungarian algorithm to match prediction to the track frame by frame in an online manner. And then, because in offline applications, ReID could reduce identity switch by reconnecting broken up tracks, we define that 2 tracks without overlap frames in time within n frames apart and with frame similarity higher than theta will be connected. The dataset for evaluation are MOTS-20 and Kitty MOTS datasets. The performance of DIOR in the MOTS-20 benchmark is shown in this table. Comparing to the baseline track RCN method, we significantly increased the number of mostly track and reduced the mostly loss to a large extent. We also achieved promising performance in the Kitty MOTS dataset on both pedestrian and car categories. As a supplement, here we show the tracking-only performance based on the BMTT challenge in CVPR 2020. The proposed tracking method won the first place. Here are 2 pedestrian tracking demos. and vehicle tracking demos.